video, I want to talk about the sampling distributions for the difference of proportions and the difference of means. So really, I just want to preview kind of what in the world is even happening in this unit. So as you're doing these confidence intervals and as you're doing these hypothesis tests, like what is really happening in the background and what is really going on. So what we kind of know at this point in statistics is sampling distributions drive kind of everything we do, okay? We can make confidence intervals based off sampling distributions. We can make hypothesis tests off it. Sampling distributions kind of drives everything. So what I want to do is I want to talk about what do these sampling distributions look like when we're looking at a difference of means and a difference of proportions, and then also tie it together with what does the confidence interval and what does the hypothesis test look like. So let's start with two proportions. So we have two proportions and we're making a comparison between the two. So here's how the sampling distribution kind of works. We have two different populations. So maybe I have one population that has a proportion, maybe I have another population that has a proportion. What we want to do is we're going to create a sampling distribution of p hat 1 minus p hat 2. Here's what that means. I'm going to go to this population, this first one. I'm going to grab some sort of random sample and get a proportion from that random sample. You know, maybe 17 out of 33 do blah, 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 blah. Okay? Get a proportion from the first population. I'm going to go to my second population. I'm going to get another sample. It does not need to be the same size, but some sort of sample. Get a sample proportion from there. So I have a sample proportion from the first population. I have a sample proportion from the second population. What I'm going to do is I'm going to take the difference of those two sample proportions. So take my sample proportion, subtract a sample proportion, find the difference. Figure out how far apart are my two proportions. That difference is what is going to create my sampling distribution. So slowly, I'm going to go to a population, grab a sample, get a proportion. Go to a different population, grab a sample, get a proportion, find the difference, add that difference to the stack. Do it again. Sample, sample, proportion, proportion, find the difference, p hat 1 minus p hat 2, add it to the stack. That is me creating the sampling distribution. Now, what we know from the sampling distribution is we could talk about where the center of that sampling distribution is, and we could talk about its spread. So these are things that are on the AP formula sheet as well, that they give you this information. You can go to the two proportion part. They're going to tell you the center of this proportion is P1 minus P2. Okay, so the center of this sampling distribution of p hat 1 minus p hat 2 is P1 minus P2. The standard deviation is the square root of P1 times Q1 divided by N1 plus P2 Q2 divided by N2. And I talk about where these formulas come from in class. For this video, I'm not going to go into that full detail. That's what creates our sampling distribution. From there, we can use this knowledge of this sampling distribution, the collection of all these differences of p hats and p hats 1s and p hats 2s, and we could run confidence intervals and we could create hypothesis tests. Kind of the rule of thumb with it is if the problems give you information about p, which is the population proportions, use p. So if you have numerical values for p, p1 and p2, use them, okay? Use them in this formula. If you don't, and that's where the standard error comes in, the next best thing instead of the population proportions is these sample proportions. Those are our p hats, okay, our sample proportions. So that's kind of the rule of thumb. So when you're running down a confidence interval, what we're trying to do is we're trying to pin down the difference of P1 minus P2. I want to figure out how far are my two population proportions. How far apart are they? That's the purpose of the confidence interval. Now, since I don't have a numerical value for P1 and P2, you're going to see some substitutions of p hats. So the formula there is you're going to find the difference of my sample proportions, p hat 1 minus p hat 2, plus or minus z star. And then for the standard error there, we are going to use this same standard deviation up here, the sampling distribution. But remember, we don't know P1 and P2, so we're using the next best thing. Instead of P1, Q1, we're using p hat 1, Q hat 1 over N1. We don't know P2, Q2, so we're going to use p hat 2, Q hat 2 over N2. That is going to create us a confidence interval so we can get a pretty solid idea of just how far apart are my two population proportions. For the hypothesis test, what we're going to assume is our two proportions are equal. So one population's proportion is equal to another population's proportion. That's what we're going to assume as the null hypothesis. We're going to hold that true until we could dispute that some other way. What we're going to do in our alternative is you're going to make some sort of comparison between P1 and P2. Maybe someone thinks P1's bigger than P2. P2 is bigger than P1, or the argument of, hey, they're just not equal, okay? Rule of thumb, if you know P, use P. If you don't know P, use P hats, okay? So we're gonna do our observed. We're gonna do P hat 1 minus P hat 2, and then we're gonna subtract P1 minus P2, okay? So P hat 1 minus P hat 2, P1 minus P2. On the bottom, there's this P hat C, Q hat C, which is a little bit different. It's based off this idea right here that P1 equals P2, okay? We're assuming P1 is equal to P2. So what we're gonna do is there's this thing called P hat C. If we're assuming the two proportions are exactly equal, the sample that I got from P1, the sample that I got the other proportion, we're just gonna combine them together, hence the subscript C. So I'm gonna take my two samples, push them together, and make a big combined sample proportion. That's P hat C, okay? So we're gonna have P hat C, Q hat C divided by N1, P hat C, Q hat C divided by N2. That is gonna be my hypothesis test. So you could see and kind of compare the similarities to the center and the standard deviation of the sampling distribution. That's the groundwork for how we do our confidence interval and hypothesis test. Let's talk about means now. So two means, there's two types of problems. There's paired and unpaired. Paired and unpaired. Paired is very, it can be deceiving, but it's not too bad. It's gonna try and set itself up like you're comparing two populations. You're not. The data is paired together, and the common comparison I use is like ACT prep courses, okay? In an ACT prep course, you might start the class, take a practice ACT, figure out your score. You do the prep course, learn how to do the ACT, all those things, and at the end of the course, you take another ACT to see, hey, how did I improve? How did I improve? It's the same person doing the test, so it's not two different populations comparing. It's really the same population both times, okay? But we're making that same population do two things at once, which is why it appears like it's a two sample problem. It's not. It is one sample problems in disguise. That sampling distribution, it's just, hey, I'm gonna go out and get a sample, and for that sample, I'm gonna have you take the ACT at the beginning of the course, take the ACT at the end of the course, find your differences, and I'm gonna take the average of that. So it's a single data set, not two data sets. It's a single data set of growth or differences there. The center of that sampling distribution is just mu equals mu d. So the center should line up with mu. The standard deviation should align with mu d divided by the square root of n. This sampling distribution is very similar to the one sample sampling distributions. The only difference is we have this subscript d for the differences, okay? The confidence interval hypothesis test, again, they're very similar to our one sample t procedures. They're very similar. We can pin down mu d, so we can pin down, all right, for these paired, situations, how big is our differences across this single population? So x bar d plus or minus t star st divided by the square root of n. Very similar to a one sample t interval. For a hypothesis test, what you're going to assume is you're going to assume your before, your minus, your after. There is no difference. There is no difference in my before data and my after data. There's no change. What we're going to try and argue is, oh yeah, there is a difference. It went up, it went down, just not what you say it is, whatever. Very similar to a one sample t test. So t equals x bar d minus mu d divided by st divided by the square root of n. These are paired t tests, which is really just one sample t in disguise. I like teaching it, I like bringing it up, because they can appear like a two population problem. They're not. It's the same population that you're dealing with. Our final problem I want to talk about is the two means which are unpaired. Okay, two means that are unpaired. Let's talk about what this sampling distribution looks like, and then we'll get to the confidence interval hypothesis test. The idea is I have one population that has a population average. I have a different population that has a population average. What I want to do is I want to compare these two populations and their averages. So we could create a sampling distribution, ooh, that's a little bit of a miss right there, of x bar 1 minus x bar 2. Okay, a sampling distribution of x bar 1 minus x bar 2. So let's just roll with the idea of ACT scores. That's something easy for high school kids to comprehend. Maybe I go to school A. I go to school A, I get a random sample of however many kids, and I find that sample's average ACT score. I go to a different population, a different school. I get a sample over there. I get their average ACT score, their X bar. So I got a sample X bar over here, a sample of an X bar over there. So I have two sample ACT scores. What I'm gonna do is I'm gonna find the difference between the two. Take my first sample's average, subtract my second sample's average. That's what's gonna be added to my sampling distribution. I'm gonna throw that on the pile. I'm gonna take the X bar 1 minus X bar 2, slap it on the pile. And I'm gonna do that again. Go to the first population, get a sample, get its X bar. Go to the second population, get a sample, get its X bar. Find the differences of my X bars, slap it on the stack. Over time, I keep repeating this process over and over and over. I create this sampling distribution, which if we follow all those assumptions, yes, it is going to be approximately normal, which opens a whole world of things for us. What we know, and also what the AP formula sheet's going to show and share with you, is we know the center of this sampling distribution. We know the center of all these X bar 1s minus this X bar 2. So there's a ton of X bar 1 minus X bar 2, X bar 1 minus X bar 2. We know the center of this sampling distribution is just mu1 minus mu2. We know the spread of this distribution through the standard deviation. We're going to take sigma 1, square it, divided by n1. Sigma 2 squared divided by n2. Remember, sigma is the population standard deviation. Mu is the population mean, okay? So that's what the center of the sampling distribution is. That's what the standard deviation is. Reasons why this is relevant is if you know mu, use mu. Mu is the population average. If we don't know the population average, we're going to use X bar instead, a samples average. It's a good substitution. If you know the population standard deviation, so our sigmas, use it. If we don't know the population standard deviation, a good substitute, which is what gets our standard error, is use this sample standard deviation instead, which is represented as S. So the confidence interval here, what it's trying to do is pin down where mu1 minus mu2 is. The entire school average of an ACT of school 1, how different is that than the average ACT score of the entirety of school 2? We're trying to pin down how big of a difference in ACT scores is there from my population at school 1 minus my population at school 2. That's essentially what you could do with a confidence interval. So we don't know mu1 minus mu2 because if we did, we'd just subtract them and say, here you go. So we're going to substitute X bar 1 minus X bar 2. Take my two sample means, subtract them. X bar 1 minus X bar 2 plus or minus a T star. For my standard deviation, it's very, very similar to this one, but instead of using sigma, we use S. I don't know my population standard deviation, but I do have sample standard deviations. So we're going to have the square root of S1 squared divided by N1 plus S2 squared divided by N2. And then finally, we have hypothesis tests. What we're going to assume is that these two population averages are the same. That is our null hypothesis. What we're trying to prove in our alternative is we're going to argue maybe mu1 is bigger than mu2. Maybe mu2 is bigger than mu1, or we're just going to argue they're not equal. So we're going to make some sort of comparison between mu1 and mu2. So we're going to take our observed minus our expected divided by our standard deviation. Observed, that's what we got in our samples, X bar 1 minus X bar 2. What we expect to happen is the population averages, mu1 minus mu2. Now, for the standard deviation, again, we're not going to have these sigmas. We're not going to know the population means, so what's a good substitute? Sample, sorry, that's called these population means. We're not going to have our population standard deviations, so what's a good substitute? Sample standard deviations. So we're going to have S1 squared divided by N1 plus S2 squared divided by N2. You can see this is what the AP formula sheet gives you And you can see a lot of similarities of, okay, I understand where we went from here to these formulas. I can put them together. So that's just an explanation of kind of the basis, the groundwork of this entire comparing proportions, comparing means unit, okay? It's the groundwork of how these sampling distributions came about. So there you have it. Yeah, watch through it. It's a lot to handle, but that is the inner workings of how this unit works.